Hi, this is Alex from devstories.eu. NVIDIA NeMo Guardrails, Episode 5 of 10. If your retrieval augmented generation system ingests an unredacted employee database, you have already committed a compliance violation before the language model even generates a single word. Once sensitive data enters the prompt context, you lose control over where it goes. Dynamic PII detection and masking is how you intercept that data in transit. Let us look at an internal human resources bot. A manager asks the bot a general question about the company performance review policy. The bot searches the internal knowledge base. The search returns the relevant policy document, but the retrieved text chunks accidentally include a specific employee record appended to the file, complete with a name, a home address, and an email. If the system passes those retrieved chunks directly to the language model, that sensitive data becomes part of the context window. NeMo Guardrails handles this by sitting between the components of your application and filtering the text stream. It provides two distinct approaches. Detection involves identifying personally identifiable information and taking a hard action, such as blocking the prompt entirely or throwing an error. Masking is more flexible. It finds the sensitive information and replaces it with a generic placeholder on the fly. The text john@example.com becomes a bracketed string saying email. The underlying database remains completely untouched. To execute this, the guardrail system relies on specialized external tools. You configure the framework to call an engine like Microsoft Presidio or GLiNR. Presidio typically uses pattern matching, regular expressions, and rule-based logic to spot standard formats like phone numbers or credit cards. GLiNR, which stands for Generalist and Lightweight Indicator for Named Entity Recognition, uses a small machine learning model to identify entities based on the surrounding context. You define an array of entity types you care about, and the selected engine handles the extraction. This protection operates across three specific points in the application flow. The first is the input rail. If a user types their own social security number into the chat window, the input rail scans the incoming string and masks the number before the language model ever receives the prompt. The model processes the request using the placeholder, completely blind to the actual number. The second point is the retrieval rail. This is the part that matters. When your system queries a vector database and pulls back raw text chunks, the guardrail intercepts those chunks before they are injected into the final prompt template. It scans the retrieved text, strips out the real names and addresses, and substitutes the masked tags. Your retrieval mechanism can pull from messy, unredacted data sources, but the language model is shielded from the sensitive details. The third point is the output rail. If the language model generates sensitive data, either by hallucinating it or because a piece of data somehow slipped past the earlier rails, the output rail acts as a final checkpoint. It scans the generated response and masks the sensitive text before it reaches the user's screen. Because all of this happens dynamically in memory during the execution of a single request, your data architecture doesn't have to change. You avoid the massive engineering overhead of maintaining duplicate pre-redacted databases just to run a chat application. The most secure way to handle sensitive data in a language model application is to ensure the model never computes on the actual data in the first place. That is all for this one. Thanks for listening and keep building.